Okay, so this is the source code. So what we're going to do first is to run the branch node table. So let me just run the branch node table of each of every cases. Okay, so we're going to run it. Case 1. Okay. So this would take for a while, though I've already run everything before I start the record, but for the sake of this recording, we're going to show the running of each cell one by one. So we are done with I think with case 15. Okay, so when I'm doing this code, this would take so much of my time to be really detailed, and was able to also validate it from Excel. So first, I already try to do the simulation on Excel and then put it here on the code or on the Python programming. So I already validate the results from an Excel simulation. So yeah, so we are down to the algorithm 2. So here in algorithm 2, all the branch table of each cases was already simulated. So on algorithm 2, uh, the program will ask for cases that this branch or this program wants to simulate. So let us just so here. So the user input is asking for the case number. So say we want to know case number 1. So just type 1. So this will be the result of the uh, primary and backup relay pairs. Okay. So now what we're going to do is to read the relay settings. So what I have here is the Excel file or the CSV file wherein the load flow results and the short circuit results are in there. So the program will read those results for the computation of the A coordination matrix and the TDS setting. So that's what this cell is about. And then, so it gives you a table of alpha, beta, OLF, load flow, and short circuit ampere. So that's basically the relay settings CSV. So and then the cell will ask for OLF, so that's the overload factor. That's a 1.5. So we use 1.5. And then next one is the load flow analysis. So these are the what we need. So these are the pickup values or the pickup current. And then for the short circuit analysis, we have the fault current. And then the program will ask for M. Okay, so that's it will compute for M. That's the plug multiplier settings, and the formula of that is the short circuit current over the load flow current times the overload factor. So these are the results, and then it will ask for the beta, the computation of the beta. The beta is predetermined, and that's 0.14 for standard inverse. Also for L, that is 0, and then for alpha, that's 0.02. Okay. So I put here M alpha, that's the that's the product of M times alpha. And then we go to the A coordination matrix, that's beta over uh, M alpha minus 1. Okay. I'm sorry, M alpha is M raised to alpha, basically. So yeah, so this is the computation of A coordination matrix. Okay. So next one is so we print the A coordination matrix for relays 1 to how many? Relays 1 to 64. Okay. And then print again. Okay, so we print the A coordination matrix here. And then we have the A coordination matrix for primary and backup. So since we already got the results for primary and backup, we're going to get uh, the program will print for the A coordination matrix for each of the primary and backup relays. Okay, next one, it's also printing the A coordination matrix. Okay, all right. So let's just skip this. Okay, let's just skip this for a few. Okay, so X is the TDS. So basically this is the time dial settings, the result of the time dial settings. And then Y, okay, you can see there the value of Y here. The value of Y is the TDS setting for backup relay. So X is for primary and Y is the backup. So you have a tabulated results here for the TDS results and the time of operation. So time of operation is TDS times the A coordination matrix. So TX is the product of A primary 1 times X. And UY is the product of A backup and Y. Okay. So next one is, okay, these are just validation. So Z, okay, Z is the coordination time interval. Okay, and then we again generate uh the time of operation, and then skip this. Let's just skip this. And this is the time that we're going to we just generate the X and Y again. Okay, I believe this is for the artificial neural network already. Okay, so this is the X train is equal to X, so that's the TDS that we're going to optimize, and Y train is equal to Y, so that's the TDS of backup. Okay, so this is the training proper. So this is where the program of artificial neural network come into the picture. So you can see there the input. Okay, so this is the input here in this cell, and these are the neurons. So you can see there 128 by 8 neurons. So you can see there here the neural network itself. Now what we're going to do is to compile, and then so let me just skip this. So we're going to uh, train the network using Liebenberg-Marquardt algorithm. So let's just wait for the training. So basically, I also include the training using ADAM because these are the basic training, but I also include the training using Liebenberg-Marquardt. So yeah. So let's just wait for the training. So you can see there how the program learned and optimized the input. Okay, our input for the neural network. Okay, it will just take a while. Okay, I think it's already done. So let's just run it. Okay, so it will give you an output. Okay, so it will give you an output here as the optimal TDS. So these are the optimal TDS for case 1, I believe. Let's just okay, we're going to no. So those are just the those are just the Z data, which is the coordination time. I'm sorry. That's not the TDS already, but these predictions are the optimal TDS. So these are what we're going to put on ETAP for protection coordination. Okay, so we're going to run the testing and validation. So we can see there the plot, the accuracy of testing and validation. So we can see here, we can look for the MSC. What's the MSE? Let's check for that. Okay, on training uh the neural network using Levenberg-Marquardt, we can have a mean squared error of 7.7311. So it's very close to a zero. So we can say that the neural networks was successfully optimized the TDS. So yeah, so this is the program. So thank you for watching the recording.